Let's get started. Close enough to 9 o'clock for me. Thanks for coming. I'm Bruce Oberg from Sucker Punch Productions. The talk is The Picture Worth 1,000 Bugs, a system for rigging complex game missions. We're the producers of, let's see, the Slide 2 Band of Thieves project. That was basically what I'm going to be talking about today. I was the lead programmer for that. This was released last fall. Hopefully you all own it. By applause, how many people played Slide 2? Okay, a few. Slide 1? Okay. How about everybody, just so I know what the baseline data is? Okay, all right, Doctor. So this is Slide 2 is an action-adventure title. Hi. It took about 2 years to make. We had 35 people working on it. As you can see, the vast majority of these people were artists and designers. We only had really a coding team of 10 people, and we broke those into what we call riggers and engine coders. And then, of course, we also had a QA department that tested the game every single day. I'm going to talk basically about a system for helping out those 5 rigging coders, the guys who actually had to rig missions. So what are we talking about? I'm going to explain a little bit of the title here. So after this slide is when you can decide if you want to cut out early, because I'm not talking about something that is interest of you, because I didn't write the abstract well enough or something like that. I'm going to talk about rigging. Some people call this scripting. It's not engine code. It's typically code in between above the engine, usually running in a scripting language. For our purposes, this was the gameplay code for objectives in the game, for things that we wanted the player to accomplish. It's not in the engine. It wasn't written in C. It's compiled with the artwork. So when our riggers are working on a particular mission, they'll write some rigging code. They'll rebuild possibly just the code, possibly also the art associated with a level, and then run it on the console, and they'll be able to test it out. It's written in Scheme, which is kind of a Lispish language, and you'll see some of that later on. Complex game missions, again, from the title. In Slide 1, all the missions were like missions in, say, Crash Bandicoot, which we were compared to, which meaning that you went into a particular piece of geometry, like a level, a room, and the mission was just about how to get through that room or how to get to the end of a particular level. In Slide 2, we knew that we wanted to have a larger world where lots of different missions would kind of be happening all on top of the same world. You can think of, like, we had Paris was the first major level of Slide 2, and there's lots of buildings that Sly can run around on, and lots of different missions are kind of becoming available and going away when you complete them, all using the same geometry, not unlike kind of what's done in GTA or Zelda. We knew that different missions were going to have kind of sophisticated setup where you're going to have to put a bunch of things in place. Different missions would be succeeding, failing different ways. We knew that a lot of missions we'd want to be able to say, okay, go kill these 6 different guys, and we didn't want it to matter which order the player did it all in. And then when you were done with a lot of these missions, we wanted the world to kind of change in some way. The canonical example is, Sly has to sneak in and open up the gate that's going to, open down the drawbridge over the moat so that everybody else can go in and help him. And we wanted a way to kind of express all these types of things in a single system. So we needed a system for organizing all the code associated with all these missions. Wanted to be able to jump to missions really quickly. This is kind of super helpful for debugging and for testing out stuff. We wanted checkpointing to be built in. So what happens when the player dies or there's a failure condition? You want to reset the player back to something, some earlier point in the current objective. We didn't want missions to have to really know a lot about each other. When we first started coding Slide 2, we didn't have the system in place, and we had a lot of intermission kind of corrupt, as I would call it, where the code for a mission later on would kind of have to refer very explicitly to objects or data that had been saved in our persist state for other missions. And we thought that that kind of cross-mission stuff was encumbering to us. It wouldn't let you, it took away your flexibility in, like, say, moving missions around if there was a lot of cruft like that. And finally, how you stored your persisted state on the mem card was actually a pretty big driver to how we put together this system. We put together a system, and it turned out to be super great for debugging how these missions worked and helping keep the rigging programmers really, really effective. Just be able to always keep on making progress and do lots of iteration, tweaking things, having designers come talk to them and say, well, this is a little bit bad. This isn't fun. Let's see if we can tweak it. And our system was great for being able to debug things and iterate over them that way. And we also came up with a great visualization of what a mission and kind of the entire structure of the goals in the game all look like, which is the valuable picture that I mentioned in the title. Here is one of the valuable pictures. I'm not going to get into details about this right now. We're going to come back to this later on. I'm going to give you a bunch of details about how all this stuff is put together. We'll come back to it, and I'll kind of zoom in on some stuff so you can see what's going on. Think of this, though. This is a snapshot of the state of a player during the game while they're in the middle of gameplay. And we could generate these super fast, and they're super useful. More to come later. By applause, how many people know just off the top of their head when I say the word DAG what I'm talking about? Applause. Okay, about half of you. All right, the DAG is a directed acyclic graph. It's a mathematical concept. If you don't know about it, you should probably leave and go read about it right now because it's very important. A DAG is a set of nodes with arrows. The slide 2 DAG, which was what that picture we saw just before was, each node of this directed acyclic graph is a task, a small gameplay item. If any of you saw Raph Koster's talk about game atoms, I kind of was getting deja vu when he was talking about kind of indivisible elements of gameplay, or yesterday Cliff's talk about game loops. Those guys are both talking about kind of theoretical concepts of what a small chunk of gameplay really is. This is actually, in our system, this is actually something the player can do that they have to accomplish, like open a door or kill a guy or steal something. In addition, above and beyond just being a regular DAG, the slide 2 DAG has a state associated with every node in the DAG. And here are the 4 states. We're going to be talking about these a lot, so try to memorize them. The first one is unavailable, which makes sense. A node cannot be done, can't be completed, is another way to think about it. Available means it can be completed. Complete means it has been completed. And final is a state that we used. I'm going to get more into it later, but for now, think about it as mostly just like a complete state. Complete and final. For the purposes of the first half of the talk, they're basically the same. We used colors. You saw a bunch of colors in the picture earlier. And these colors are kind of canonical colors that we associated with these different states of every node in the slide 2 DAG. And so, again, these colors, it'd be good for you to kind of put them in your head. They kind of make sense. Red for unavailable. Green for, yeah, it can go. We're ready to go. Complete means it's done, and gray means it's really, really done. Final. Okay. Now, in addition to every task, every node in the DAG having a state, we also have some rules about the interrelationship between states of DAGs that are adjacent to each other in the DAG. This is all going to be words. Don't worry if you don't get it. There's going to be some pictures coming up very soon that'll explain it all. So, like you would think, every node in the DAG starts off as unavailable. They all start off red. By convention, we actually we say things that don't have any pointers into them, things at kind of the top of the DAG, actually start out unavailable. But you'll see that in the picture later on. Tasks, nodes in the DAG, become available once everything before them, everything that points into them, their predecessors, become complete. Similarly, everything that's before an available task has to be complete, and everything that's before a complete task also has to be complete. This is kind of going forward in time. All the successors of tasks that are available have to be unavailable. And also, all successors of unavailable tasks have to be unavailable too. I know there's a lot of words and it doesn't exactly make sense, but we'll draw some pictures right now to make sense. So here's a DAG. The dots are tasks, nodes in the DAG, and the colors indicate the states. And this is a DAG in the slide 2 system. Starts off with everything unavailable except for that first one. It doesn't have any predecessors. It doesn't have any arrows coming in, so it starts off as available. At some point in time, to be discussed later, something somewhere tries to make that first task complete, tries to request that it becomes complete. And when that happens, the first task is made complete, and then the engine, the underlying system running the DAG, also marks the second task as now being available. So that second task became available because everything pointing to it, it's the one on the top, became complete. So now another completion request can come in for that second task. And it completes, and then automatically the state of the last task, the last node in the DAG, becomes available because, again, all of its predecessors have become complete. And then, of course, you can complete the last one, and then everything is all complete. Okay, so this is another DAG. This is less simple than the other one. So this DAG, we have a fork going out, and then a kind of a collector coming back in. And when that first node is made complete, it becomes complete, and again, automatically, the two below it become available. Both of them, all of it, from the perspective of each of those tasks, all their predecessors became complete, so they're now available. So now let's say another request comes in to complete that task. It becomes complete, but you'll notice that the one on the bottom did not become available because from his perspective, there's still something else pointing to it that has not become complete. So when that finally happens, that's when the last task on the bottom, it can become available only when all of its predecessors are complete. These rules are completely arbitrary. We made them up. You could make different rules for how you deal with the completion, how you make a particular task available. You could say, well, maybe 3 out of 4 of my parents should be complete. That wasn't our system. I can talk about how the variants introduce other kinds of problems later on. Okay, so those little blue stars that I was showing were kind of requests. They were completion requests. And they kind of come from all over. They can come from triggers that you've actually authored in the art, in the world, in the geometry of the world. Sometimes you play a sequence where that's running a cutscene, and at some point in time, it can say, "I'd like to complete a particular task," or maybe at the end of the sequence, "I want to complete a particular task." Sometimes tasks actually complete themselves in kind of warped, self-referential scenarios. But these requests can kind of come in from anywhere, and the DAG really doesn't kind of care who or where they're coming from. It keeps track of who they're coming from, so you can kind of make decisions. But everybody just makes kind of requests to the global DAG maintenance system. If a request comes in and a task isn't in the available state, we just drop it on the floor. It's actually very, very convenient because with this way you can actually, by just dropping on the floor, not kind of throwing errors or getting confused, you can have a volume button, say in a world, a volume that the player can walk into, a trigger, and say, this trigger completes a bunch of different tasks. And only the tasks that are available, that are really ready to be completed, can be completed. And you don't have to have logic inside the trigger volume to actually decide, well, should I make that task available or not? Or should I complete that task or not? It just works whether or not the task is in the right state. So let's show another picture. So again, this was our little simple DAG. A request can come in for that middle task, and nothing happens. But then if another request comes in later on for the one that is available, then it does get complete. Similarly, if another request comes in for something that's already complete, nothing happens. But then, if it comes in for that, for the available task, then it works. Okay. So looking at this is a more complex DAG than I've shown before. But the way to think about progress of the player through the game in this system is like this kind of front of available tasks. Remember, the rules are that everything before an available task has to be complete, and everything after an available task has to be unavailable. So there's this, as the player kind of does stuff, these little green dots are moving down through the DAG of all the possible things that a player can do, and kind of turning on things that now are available for the player. So this, if I could pick one slide, this is the most important slide of the entire talk, of having this kind of this front of available tasks moving through the DAG. Okay, so that's a bunch of dots and lines and colors, and what does it really mean? Okay, all the gameplay code in slide 2 is attached to these tasks, to the dots in the DAG, as callbacks. So there are different types of callbacks, like when the state of a task changes, when it becomes available, when it becomes complete. A callback is called to the actual task, and then code is attached to that task for the particular callback, and then the code can do stuff. It can put things in place. It can take objects in and out of the world, start a cutscene, whatever it wants to do. Sometimes the engine is actually triggering events and signals that are delivered to the task, again as a callback. And then there's other signals that can be done that I'll talk more about later. So these callbacks do all the real work. Like I said, triggering cutscenes, object management, all the real work. Okay, so everybody hold your breath. We're going to try a real live demo here. Okay, great. So this is slide 2. I'm only going to show you a few seconds of the beginning of a level that we called France, and I'm going to tell you kind of what's happening. While there's not a lot of player control going on, but the DAG is controlling a lot of it, so hopefully I'll be able to narrate this well. Loading. Okay, so the DAG has been loaded, and that very first task was made available, and it decided to to start the cutscene that we're showing now. That means playing an animation on the camera, putting Sly in place, walking across the top of the roofs. There's guards on the other roofs and a guard down below. Those were all put in place by the DAG. By this one, the sequence is playing. The sequence gets all the way to the end. It puts Sly into the safe house, and the sequence is over, and it's completed that first node in the DAG. And now the second node in the DAG is actually available. At this point, the player's in control. I can't do much. I'm just choosing between either Sly or our little thief net thing. But the player is control, and that second DAG is kind of waiting in the available state. As soon as I hit X, which I'm going to do right now, Sly exits, and there's a volume trigger right outside that door that says complete that second DAG node, that second task, which in turn kicks off a new cutscene. So this is a cutscene where we go into kind of a peek mode. The characters can talk to each other. The camera's going to slide over to the left here in a few seconds. You can see off in the distance there were some words there, that satellite sabotage. That's actually the next mission it's the only mission that's available to Sly at this point in the game. But that geometry, the word satellite sabotage and the waypoint, the thing that took to it, is actually attached to the next DAG node, which has become available about halfway through this cutscene. It marked the second task complete, which made the third task available. And now that task is available, the waypoint is there, and Sly can go over and start the mission. Now, you'll notice up top that a little bit of help just appeared, like use the right analog stick to look around. That was there was a task again to turn that on after a few seconds if the player hasn't already done that particular control. And it was attached to the DAG at a point after the player had been on the roof. So that once the player was off the roof, we knew that it was time to possibly play that help sequence. And here we are, we're at an entrance to a mission, and this again attached to a DAG node, and ready to go for Sly. As soon as Sly jumps in there, we'll complete that node and kick off another cutscene and actually start the next real mission. Okay, so end of first little mini demo. So what was happening? I talked a lot about it while we were doing. I'll run through it real quick. So there was the run-up. The first part was Sly running on the roof. There was the roof intro where those two guys were talking, and then the satellites mission at the very end. The run-up, the first task was set to available. We started a hands-off sequence. We took away control from the player. We put in the custom camera, put all the players in place. At the end of that, the run-up task was marked complete. So now it's complete. The second task was marked available. As soon as it was marked available, the player was in control. And as soon as I hit X to go out the door, then the safe house, then that second task was marked as complete. Once it was complete, it kicked off yet another cut sequence, which started the little Binocucom dialogue. And that satellites mission was available about halfway through so you could see it during the dialogue. Okay. So I've talked about tasks, but originally in this talk, I said I was going to talk about missions. And so the way to think about a mission is just a contiguous group of tasks in the DAG, a sub-DAG of the tasks. We made a rule that there was only one entry and one exit task to it because it makes it convenient for knowing where to attach those waypoints for a start mission. And if you only have one exit, if you kind of enforce the rule, there's only one exit task, only one task at the end of the mission, then you can know when it's complete, when the player has actually finished a mission, and you can do all the kind of reward animations and woohoo stuff that goes on at the end of a mission. So when when the exit task becomes complete, then we actually mark all the mission tasks as final. Here's the distinction between complete and final that I kind of alluded at earlier, which is when a task is complete, we actually may turn it back to unavailable or available. We may wind back time eventually. But when a task is marked as final, we don't ever expect for it to ever go backwards in time again. So here's a graph. So here's a DAG with some states, and I've just drawn a little box around, that's a mission. There can be lots of tasks that aren't associated with missions for maybe things you want to do in between missions. In this case, there's some over on the right, but this is a mission. As the player makes progress in the mission, you can see that we mark them as complete, the tasks. You'll see that very top task is gray. It's marked as final, and we did that for everything outside of a mission, because everything outside of a mission was something that we never thought we would actually roll back in time. So again, another slight distinction between complete and final. When we completed that last task in the mission, the one at the bottom, we turn everything to final. Okay. So everything I've talked about so far is really simple. In fact, one guy left already, which is good. He probably thought it was too simple. This is all just kind of easy stuff of just marching forward in time. You're probably wondering, well, why don't you just write this all in some procedural language or something? Why do you need to break everything up into these tasks? And the key to these tasks and the rules is that what you want to be able to do is checkpoint and debug. You want to be able to go into the macro and kind of turn it into what would it look like at a particular point in time. And the way we do that is forcing the state of a task. If I take a particular task and I say, I want this task to be available, the rules kind of tell me what the states have to be in everything else in the DAG. And so from loading the game, if I load the game without any kind of memory card data and everything, and I want to jump forward in time, I can just say, let's mark that task available, and then the DAG is all marked as available. Everything is marked to the states that make sense according to the rules. All the callbacks are called on all the tasks, setting their state to whatever state they are, and so you can easily jump through time to the point in time in the game where you need to go. So let's, right. Checkpoints in gameplay are kind of the same thing going back in time, and that if a player dies, we want to send them back to some earlier spot, some door maybe, or some location. We actually associate a location and what character with a task, and then when the player dies, we just say that checkpoint task is now available. So everything after it that had already been completed gets set to unavailable, and the player is put at the location, and they're ready to start playing the game. This is what we call a rollback. So it's rolling back in time. It's setting the state of a particular task, forcing it to a particular state, and then just letting everything else kind of happen automatically. In slide 2, sadly, doing one of these rollbacks, we'd reset the world, we'd force the checkpoint to available. We wish we wouldn't have had to have reset the world, but we did. And like it puts the character at that character location, like I just said. And you can go forward or backwards to any checkpoint at any time. These checkpoints are in all the missions, and they're part of the authoring process for, I want a checkpoint at this point in the mission, this point in the mission. But they're also the points where for debugging, we can say, I need to jump to the beginning of mission X in some episode, and that's how we use the checkpointing as a place to jump forward to. Okay, let's look at some checkpoints in action, just so we can. Okay, here we are. Oh, looks like the slide died since the last time I was here. This is the debug menu in the upper left. Something you'll never see, the players never get to see. But we have a reset menu and we have a reset to checkpoint. So this is a list of all the tasks in this episode that have checkpoint locations associated with them. We use kind of a naming scheme. T1 meant a task in episode 1 of the game. This is all episode 1. We kind of use a naming scheme where we have a word kind of mentioning which mission this was, the recon mission, the bugging mission, the followed Dimitri mission. I'm going to, if I'm sitting in my office playing a game and someone comes in and says, oh my God, we have a bug in the follow Dimitri mission, I can just choose this task and jump right to the mission immediately. You'll also notice that these guys are red, and that's actually reflecting their current state. So this list of tasks, the colors we're showing are the same colors from the graphs I was showing you earlier. So all of that first checkpoint is available, and all the rest of these are unavailable, which means in normal gameplay the player couldn't choose them. But since I'm the developer, I can shoot that one. So we're resetting the world. We're going to load everything back in. We're going to mark that first that one task that I just chose as available and put fly at the location associated with that task. And here it is. So here we go. And now, if I actually go or if I hit L3, you notice that waypoint is there. That's associated with the next task in the graph, which is available. And as soon as let's see if we can see this. As soon as I hit the bell, which is the next thing I'm supposed to do in the game, the arrow went away because because we've marked the next task is available. The task before it has gotten unavailable, and you can see that this waypoint on top of Dimitri became active because the task associated with it is available. So the task right now is following Dimitri. So I'm playing this, I'm having fun following Dimitri, and someone else says, "Oh my gosh, that's not important. We got to go fix this other problem in the pickpocketing mission." Okay, great. So go to a checkpoint. You can see that the colors are all different for the different states, different tasks. I'm going to go to the Moulin Rouge is the pickpocketing mission. So again, right in the middle of anything, we're going to reload the world. We'll jam on the DAG, set the state of a particular task to available. All the rest of the states are now set properly, and I'm now starting that mission. Down in the lower right-hand corner, you'll see a little counter thing. Because we have the DAG, because everything is kind of structured in these tasks, we could make like little helper things. Like we have a helper piece of a helper object, which we just say, you're a counter, and you should count how many nodes in the DAG are complete. And so this is telling me that 1 out of the 6 nodes that we told it, the counter, to count for this mission are complete. In fact, if I go, that we have a kind of a more broad tasks menu where I can, let's see, Moulin Power. Here's all the tasks for the Moulin Power mission, and you can see that key 1 is complete, which is why the count is 1 of 6. I'm going to go to key 2. If I wanted to get to the point where I had all but just the last task, I can kind of go through here. I can force a task is complete, and boom, the counter down there changed. And I could do this all the time. I want to do 3 and make it complete. Or maybe, wait a second, the one that I really wanted to debug was key 1, so I'm going to go back to key 1 and force him available. So the counter went back to 2 out of 6. And then, I can start debugging this mission, start jumping around, playing with players, and I can go back in time, go back to the reset menu, and if I figure out the bug, I'm going to go back to that, follow start checkpoint. And just go back to the follow mission. So this is how we can jump around between missions super quickly, super easily, and this was very, very useful. Okay. Okay, so this is the Game Developers Conference. I'm a developer. I'm going to talk about an algorithm. I haven't seen any algorithms talked about, and God damn it, that's what I want to talk about. So I'm going to talk about the algorithm we used for forcing the DAG into a coherent state. As I mentioned before, we start with a task, start with a desired state, and what we're going to do is we're going to walk backwards through all the predecessors in the DAG. We're not going to change them right away. We're going to figure out what they should be based on their current state. And we're going to kind of mark them as like eventually at some point in time we're going to this is the state we want to set them to. We're going to mark them all. And then if something's already marked, we're going to skip it. So let's see how this works. So here's a DAG here's a DAG that has the initial state. Everything mostly is unavailable except for the first one at the top. I want to make, let's see, that went forward too many times. Oh, I want to make G available. So that green arrow is my kind of initial desired state. G being available kind of implies that D, the one above it, has to be complete. Similarly, the next one above that has to also be complete. And the one above that actually has to be final because it's outside of a mission. So walking backwards, I'm figuring out what I'm going to have to do, and I'm kind of keeping track of all those guys. And I've reached the top of the DAG, and so there's nothing else left to do. Okay, so now we're actually going to go through and actually do the work of changing them. So we're going to go through that list, but we're going to go from the top down in predecessor's first order. We're going to set each one to a state, and then we're going to deal with all the states that have to change as in successor tasks as a result of the top-level task changing. So we're going to recursively walk forward through all the successors, and again, we're going to skip the ones where we already know what state it should be in. So back to where we were. We know these are all the guys, the kind of marked ones. This is our intentions. We're going to kind of say, yeah, we're going to do A first, we're going to do B second, we're going to do D third, and we're going to do G last. So I'm just building this canonical linear list of the ones I need to change. And then, now I'm actually going to actually change them. So I set A to that final state, like it wanted. That implies that C, one of the successors of A, now becomes available because all of its predecessors are complete. And notice that I skipped B because we had already marked it as something that's going to be completed later on. And because it's already marked, it's actually the next one on the list to actually have it. So now we do the stage 2 of the list. We set B. That forces one of its successors to be available. He has another successor, D, which we're going to leave alone. Then we're going to set D. He was on our original list. We're going to skip G because he's, again, already has a marked state. And then finally, we change G. And I, the guy after him, should be unavailable, but he already is unavailable, so we have nothing else to do. So from our original state of the DAG, by forcing that one task to be available, it's actually implied a lot of other change to the DAG. It's actually implied that these other two tasks, they must also be available, which isn't something that I would have thought of if I was just kind of looking at it and just writing it on paper. But because of the rules, we know that is a valid state. Those guys have to be available, and therefore the game is always kind of coherent. We're maintaining this coherency so that every task from its perspective always knows that the rules are being followed. So let's go back to the big picture that I showed at the beginning, the big ugly picture. So I'm going to zoom in on like this section. So this is from episode 3. Some of the tasks are circles, some of them are triangles. The ones with triangles are the ones that we associate with checkpoints. So you can actually say, oh, I have a checkpoint at the beginning of this mission, and then after I do a couple things, there's another checkpoint. And then after I do a couple more things, actually after I finish the entrance task, then there's we parallel out, there's 4 other things for the player to complete. In this case, it's taking pictures of things. So they can take the pictures of the 4 different things in any order they want. Once those are all done, the collector task becomes available. It probably plays a sequence and gets you down to the end, which maybe gives you an award stamp. Let's look at another section. Let's look at this section. So again, there's a checkpoint at the top, which is a triangle. We kind of bifurcated out to a bunch of parallel tasks. Those are all also checkpoints, so that if the player's collecting different keys from different guards, they don't lose that. We remember the state. You can see kind of a thick dotted line around one of the diamonds. That is the current checkpoint. So if the player dies, that's the checkpoint we're going to actually reset to. If the player completes any of these other tasks, they will become the current checkpoint. Okay, all these pretty pictures. We thought that when we were doing this originally, that we would actually make a graphical editor for editing this DAG, and we could drag nodes around. And it turns out it's a pain in the ass. You can spend a lot of time writing graphical software for drawing graphs and lines and stuff, and basically it doesn't help you. Actually manipulating the graph is something that we didn't do all that often, and just specifying all this stuff in text was more than adequate for our use, for what we needed. So all that DAG was all defined in text files. And the graphs that you see were all generated by an open source freeware tool called GraphViz. I'll have a URL for this at the end of the talk. GraphViz, this is a package made by Bell Labs, like back in the 70s or 80s. Originally ran on Unix. It's a collection of different tools for kind of showing graphs and stuff. You just spit out a text file kind of in an XML-ish type format, and then they just generate these pictures. All the white picture that I showed you, all generated by GraphViz in like 2 seconds. We didn't write any code to generate those pictures. We had the from the debug menus that I showed you earlier, the engine just walks the DAG, writes out this file in a dot format, writes out to the PC. Then on our PCs, we have a little batch thing that runs an executable that's part of the GraphViz package called .exe, and you get a GIF and you launch it, and boom, you're immediately looking at that picture with a state of where the game is. So these images became really crucial to our development. Like, you can be playing the game, and suddenly you're stuck, and you're like, wow, why can't I open that door? I should be able to open that door. Well, you can just dump out the DAG, get a picture, and kind of see maybe what hasn't been completed in the DAG. We'd attach these graphs to bugs, saying I could get the DAG into a particular state. It actually kind of turned into a documentation tool in that we'd take those graphs and print them out on big sheets of paper, and the game designers could say, wow, we have like 3 missions that are all really linear. We should have a more parallel mission that kind of mix it up, and you could reorganize all the missions kind of on an episode macro level. We could also kind of compare missions and compare episodes. And so while we didn't use an authoring environment for making that, just being able to print them out in a graphical, with a graphical mechanism was super useful for us being able to do things like, oh my gosh, this mission sucks, we're going to have to cut it. What do we put in its place? What will work out? And doing that was all great using these pictures, was easy using these pictures. Okay. We had a thing called Focus, which I didn't talk about very much. I call it our dirty secret because it's something that we put into the system that did not work out as planned. And so I'm a little sheepish about talking about it. We had this idea of marking tasks as kind of the current one. Which task has the focus? Just like the way in Windows, where a particular window has the focus, or a text field can have the keyboard focus. We had the same mechanisms for setting the focus as we did for changing task states, meaning that a trigger volume could actually just try to set the focus on a task instead of making it complete or making it available. We had a rule that available and complete tasks could get the focus, and missions also would get the focus as well. It didn't work as planned. We thought that this would be the basis for a really rich, great help system. That if you knew which task the player was on, which the available task had the focus, that would be a quick answer to what they should be doing next. And we also maintained a count of focus, how many times a particular task got the focus, which we'd use for skipping cutscenes the second time a player went through a mission. So if they've already gone through a mission, that task has already gotten the focus once. The second time, maybe you don't give them the long version, maybe you give them the short version. It turned out that we created way more tasks than were conveniently helpable, like that way more tasks than things that we wanted to give help about. So we actually did our help based on just searching through the DAG, where depending on where the player was, where the current available task, we just kind of searched forward for tasks that had help associated with them, and we just used that as kind of like what you're supposed to be doing next. And a lot of times, we actually just use this focus as a signal that something had happened to a particular task to make some code run. And so the kind of semantics of focus was that if a task already had the focus, it wouldn't get it again. If you set focus on a task that already had a focus, nothing would happen. But it was convenient to have signaling, so a lot of times underlying code would say, well, let's set the focus on a task, and let's clear it right away because I'm going to set focus again on it to signal it about something later on. So it was kind of twisted in this arbitrary signaling mechanism. And the focus, because it was being used for arbitrary signaling, kind of bounced all around and really wasn't this kind of idea of the current anything. Let's look at a task. Like I said before, they're in text files, meaning you can version check them and everything. You can do diffs on them in source control. They were compiled with the art files. Changes to missions and stuff didn't require a rebuild of the engine. And at runtime, we'd actually have underlying all the tasks would be instances of a C++ class. So this is actually a definition of a particular task. This is the second task of that Follow Dimitri mission. Remember the one where I rang the bell and there was an arrow above it? This is the second task of that mission. And so we have it a name. We kind of give it a, give it a name, right? We kind of force this to be a unique namespace. And this is kind of why we had a system for the T1 and the mission name and all that in it. This class, this in our text file says we're going to create an instance of a particular C++ class. This is the way we created lots of instances in the game. This is the predecessor. This is saying which task is before me in the DAG. So if you had multiple of these lines, that would say I have multiple predecessors, or if multiple tasks all had the same predecessor, that's how bifurcation would be specified. This is a checkpoint, the location in the world that if we have to roll back to this checkpoint, this is the location with the character Sly in this particular world. And one of the more common things you want to do is say, when a task is in a particular state, I want all these objects in the world. And so this is our kind of shorthand for that. So you could write code to do it, but this was so common that we made a shortcut. This says, waypoint boat bell. When this task is available, then waypoint boat bell is in the world. And that was the arrow kind of above the bell that I showed you. And so as soon as this task is completed, or before this task is available, that object is not in the world, and it gets brought into the world based on this task being available. You can also use the same mechanism for putting things in the world, say, after a mission is complete. So you could say, instead of available, you could say, I want some object to be in the world when this task is complete, or when this task is final, or both complete and final. And then that object would be in the world after the task had been completed or finalized. This is some Lisp code that was attached to that same task. I've completed it, or I've kind of edited it down and formatted it to fit on your screen. This is one of the standard callbacks that I was talking about. This particular callback is enter task state. So whenever a particular task enters a new state, this callback gets called. We have kind of a case statement here saying what state did I just enter? If I'm available, then we actually are going to go run some other code. This is a more complex example of putting something in the world or taking something out of the world. In this case, there's some boat where we have to run a procedure on the boat saying, turn your lights on, which probably did something complex with the textures or materials on that boat. And when we became unavailable or final, we ran lights off to turn that off. When we became complete, we also ran the lights off, but we also ran some stuff based on the focus count. So if this task has become complete the third time, we actually run a little voice reminder. So the third time the task becomes complete, meaning the player has actually gone through and completed this task 3 times, we say, well, why don't we play a little reminder? And the 4th and 5th time, we give them even more help. Why don't you go on the roofs, because that's the best place to complete this mission. So all this code is attached to just one node of the DAG, and it gets called when the DAG, when the task its states are changed. We would change some things. Having kind of a more arbitrary grouping of tasks besides missions would have been very useful. You can imagine kind of a chain of things within a mission that you kind of want all to you want to have maintenance of stuff added to the world for a whole set of tasks, and then stuff removed from the world when that set is done, or kind of generic setup and teardown of something that's not an entire mission. Also, we had heists in Sly 2, which were basically big missions kind of all stacked together. And so groups of missions, and being able to have those all, having just a hierarchy of grouping would have worked very well. There were some types of transitions that we did not standardize, that we ended up writing lots of code on every mission in the game had the same code. We commonized some stuff, but there was other stuff that we didn't commonize. We commonized the end of every mission, the stamp that's played, and the award sequence. We did not commonize what happened when you died. Every mission had to deal with that himself, and that actually caused problems. So we would have made more things standard. Like I said before, would replace focus with signals. And Sly 2 actually shipped with a couple bugs where the DAG would be in a particular state, and if the player turned off the console and then restored the game into that state, there was nothing that was actually going to complete the task that was currently available, so you were stuck. The player had no way to complete it, and so there were a couple bugs that actually shipped in the game where the players got to some point, they had turned off their machine. When they turned it back on, they couldn't do anything. We could have actually detected that stuff with some data analysis. So again, summarizing, debugging using the DAG is great. These pictures are super useful. You can also imagine taking all the changes that are made to the DAG, every change to a task, every request made, and kind of keeping it in a circular buffer. We kept it in a circular buffer so that if something kind of isn't right, you can just dump out the list of all the changes that have been made to the DAG recently, kind of post hoc debugging. Or maybe just dumping them out to a text file as you're running along. You can actually see all the changes being made. It's very easy to see what's going on by printing all those out. The checkpointing was built in. We could rearrange missions and tasks really, really easily. We had a mission at the very beginning of Slide 2 where you had these satellite dishes. You had to go up, and for each satellite dish, you kind of had to plug it in and then turn it to point at something. And originally the mission was parallel, so you could go to any of the 3 satellites in any order. We put it in front of kids, and no one could figure out what to do. It was right at the beginning of the game, and the kids were lost. They were running around the world. They didn't know what to do, and they were kind of getting frustrated. And so we turned it into a linear sequence of do the first satellite, then the second, then the third. And so that rearrangement was just kind of like moving some lines in the DAG, and then everything worked. And so we were basically able to fix a mission with very, very little work. The memory card state for Sly is basically a dump of the states of all the nodes in the DAG, all the tasks. None of the riggers ever had to worry about anything on the mem card ever. They just created all their tasks, and the act of creating tasks and creating the relationships between tasks in the DAG was basically the data that we needed to have on the mem card. Great. That's it. Suckerpunch.com if you want to hear more about our games, and graphviz.org if you want to have some cheap code, easy code for building graphs. Thank you. We got about 10 minutes before we're going to get booted out. Yeah. Yes. Yes. The sequence it was playing was not the task. The task. I'm sorry. The question was timing. And he said, well, at the beginning of the demo, I showed the cutscene is playing, and when that second task becomes available, doesn't that kind of interrupt the cutscene that's playing? Is that a fair? The answer is the cutscene is not the task in the DAG. The task is kicking off the cutscene, and the cutscene is then later on signaling the DAG that a particular task is done. But the actual cutscene itself is not encoded in the task in the node. In the task in the DAG, there's signals happening for it. The actual cutscene is a separate object in a declarative language describing what's happening in the cutscene. That particular cutscene was not interruptible. So if you wanted to interrupt a cutscene, did we ever interrupt cutscenes? Sorry? Yeah, that would be some coding in the cutscenes. Our architecture for describing a cutscene could handle signals, and so signals could actually tell a cutscene to say, "Stop what you're doing, go to the end, you're done." So that's how we could do that. Yeah, right here. Sure. The question is, were there any other semantics that we thought of adding to the DAG? I'll talk about two semantics, one that's reasonable and one that's not. One thing that the DAG cannot describe is sly1, which was kind of funny, I thought, when I first realized it. Sly1 was very much like Mario or Banjo-Kazooie, where you would complete a bunch of different levels and kind of you were collecting stars, and then you could get through a door once you got 5. And that's kind of a N of M problem. You're completing some arbitrary subset of tasks before you can kind of make progress through a bigger task. And that actually doesn't encode very well into the system that we have. And you can imagine saying, we made the arbitrary rule that a particular task only becomes available when all of its predecessors are complete. Now you can change that rule. You could say, well, maybe it's 2 of 3 or 5 of 7 or whatever. That might work. It might work, but it also introduces the problem of, well, when you want to set the DAG to a state further on in time, do you set all of the ones complete? If you're trying to force it to a particular state, which 3 do you pick of the 3 of 5 rule, or do you just pick them all? And that's kind of one of those crevices where kind of bugs can get introduced if you don't kind of test all the scenarios. So we didn't choose to do that. The other thing that is not kind of encoded in the DAG is just inventory of what the player has, what they've collected. And again, a little bit like the coins problem in Mario. The DAG, kind of what the player has, what power-ups they've collected, that's kind of a separate thing. That's like more of an inventory control. And this is more controlling the progress of the movement through time of the game. So it doesn't lend itself to that kind of stuff. Yeah, right here. We're just changing a variable in memory. I mean, for the instance of it, we're changing it, and then we're actually calling all the callbacks associated with the task. So we set the state, and then we say, okay, now there's callbacks for this one, and then we go through that algorithm I talked about, and we make sure one of the important parts of that algorithm is that we go through all the earlier tasks first. So you kind of always know a task when its callback code is being run always knows that all the stuff for its predecessor task has been done before it, which is kind of convenient sometimes to always know you're getting stuff in a known order. Yes. when we got kind of stuck. Yeah. It was just a bug. It wasn't something in that I don't think there was very many. The particular bug we found, the question is, what was the bug that shipped in the code, I think, and what could we do to fix it? Yeah, the bug was we were in a scenario where you had beaten a boss and you had to get to a door at the end. And if you shut off the game before you got to the door, then and you started back up, you would have beaten the boss, but you were put in a different location of the world where you couldn't actually go through the door to complete the last task. So you were stuck. Be able to actually analyze the references between objects in the world that signal the DAG, and be able to kind of analyze that stochastically would have helped us maybe discover this bug. I'm not sure. It was only one. It didn't happen a lot, so that was the problem. Does that kind of make sense? Okay. Yeah, right here.
Given that you're on a console, did you do any compression on the various text formats? And if so, how did you do that?
The text formats that you saw were all compiled into raw data. The first one that's how we would turn into a C++ instance. And the instances of tasks actually pretty lightweight. I mean, they have the state, they have whether or not they have the focus, they have to have what the arrows are in the DAG. But it's all pretty small data format for those. And then the code, the Lisp code, the scheme code is compiled into code. So those text files were not on the console. Those would all be used at build time of the worlds. Then when you run the world, all the data was on the world kind of compiled in. Yes. You're in the striped shirt. We did have, the question is, did we have optional tasks? And yes, you can imagine, we're okay on time? Okay. You can imagine having nodes that just kind of don't have any children, don't have any successors, and that's how we did helper nodes. And so, yeah, you can make optional ones. And sometimes you could even have ones that didn't have any parents to have kind of multiple things that you could do at once at the beginning. We didn't do too much of that. They would, actually, no. In fact, we shipped a bug that had to do with one of those not getting marked final, because they didn't have any children, so we weren't walking backwards up the right way. And so we shipped a bug where you had completed a mission, and then if you went back into some little nook and cranny of the world, you could actually complete a task its mission had already been finalized, and basically reset progress in the game. We had players play the game and then complain, saying, "Hey, wow, I finished these 5 missions, and suddenly I'm back to like mission 2. What happened?" And this was a case where we forgot to finalize a particular task, and the players were actually able to get to this available task, and then it just walked the DAG and basically erased all their forward progress, which is something you don't want to do. Yeah, in the orange shirt.
So it seems like you could maybe just save the available states and walk backwards from there and then come to that point. Is there a problem with that?
The question is, could you just save the available states and walk backwards and forwards in there? And you could. Having those counts that I was talking about was something that we thought was kind of important. So we actually saved state associated with every task anyway, the count of how many times we had focus on it. So we actually just saved the states for everything and didn't do a lot of walking through the graph at load time from the mem card. We would just get all the states and go bam, 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 bam. So you could, we didn't. Also on consoles, it's kind of nice to have a fixed memory size, and so we just chose, and literally our save file size was 20K, so it was so small we didn't worry about compressing in that area. Any other questions? Yeah, on the end. I'm sorry, I can't hear you. Can you either use the mic or speak up?
Can a task have 2 ways to complete?
I'm sorry.
Do
tasks have 2 ways to complete? Is that like, are there multiple ways that a task can complete? Is that your question?
Yes. Can a task have 2 ways to complete? like a door, we can find the key to open the door, or we can push the door.
Okay. So does the task? Typically, no. In our system, we would have tasks associated with one type of completion, and I think almost in all cases, I got a couple guys here. Sorry? Oh, yeah. So sometimes the task could be completed explicitly by a volume button saying complete this task. We actually had sometimes where we wanted a task to autocomplete, to complete itself. So okay. So yes, there are multiple ways to complete some tasks, but most of the time it was just one way to complete a task. And we can talk about more details on the white pad if anybody. Any other questions? Yeah, in the plaid. We used our own. We made our own. I mean, that's kind of why we did Scheme, is because it's easy to compile. Yes, in the black.
Why'd you have to reset the world?
Because we're lame. With a certain amount of work, we could have not reset worlds. It had more to, the question is, why didn't we reset worlds? Why did we reset worlds all the time? It had more to do with other subsystems that we had in proxying in instances of enemies and objects. That whole scheme didn't work as well with the DAG system as we would like. And so resetting the world gave us a clean slate. We're working on that. Anything else? We're almost out of time. On the end, yeah.
Do you have any academic work that maybe informed your work that you could talk about?
I would recommend Sedgwick's book on computer algorithms. He has a great section on just manipulating DAGs. But I mean, the math part of this is dead simple. This is like 101 graph theory stuff. So it's not super complex. The strength is having these states and the rules associated with them on top of a DAG. That's what really makes the power. And we hadn't seen anyone talk about that or anything. All right. I'll be up here if anyone else has any questions. Thank you. Didn't make it in.